So this video is going to go through the three basic types of integration that we deal with in math applications at interpretation standard level. So we have indefinite integrals, definite integrals, and indefinite integrals with a bound. So all of these three ideas stem from the main idea of our integration rule. So if I take the antiderivative, or the integration, of kx to the power of n dx, remember this dx is just telling us with respect to what variable are we integrating. Or in our definite integrals, it's telling us that we're being bounded by the x-axis. So this is just for information. We don't do anything really mathematically with it when we are taking our antiderivative. So the integral of kx to the n dx is equal to, keep our coefficient out front, take our variable, add one more to the exponent, and then divide by that new exponent. So remember, integrals is just derivatives backwards. It's us undoing derivatives. So if you think of our derivative rule, so if I had ax to the power of n, let's say y equals, well, its derivative, we multiply by the exponent and we take one away from the exponent. So you can see we're undoing that. I'm adding one back to the exponent and I'm undoing the multiplication. You can also see we have this adding a constant. This is again because if I take the derivative of a constant, so if I have y equals a constant and I take its derivative, we end up with 0. So it means there may have been a constant here that I didn't know about that disappeared or turned into 0 when I took the derivative. So we always have to say there might have been a constant here, but I'm not 100% sure, so we put plus c. This comes very important in our bounded ones where it wants us to actually find c when it gives us some extra information. So let's try a couple of these. So this first one wants us to find the antiderivative of x cubed minus 3 divided by x squared. Well, first problem I can see is this x squared in the denominator. So we have to move that up to the numerator so that we can apply this rule over here. So I'm going to take the antiderivative. Nothing is going to change in the x cubed minus 3. But we're going to apply our exponent rule, and we're going to make this exponent negative and bring it up to the numerator. And now I can apply my antiderivative rule. So you can see I'm no longer going to write the integral. So I'm going to no value of k, so this is going to be x, 3 plus 1, being divided by 3 plus 1. Keep the 3 out front. X, the negative 2 plus 1, negative 2 plus 1. So we can simplify this by grouping our numbers out front and seeing if anything simplifies. So this is going to be 1/4 x to the power of 4, nothing to simplify there, minus, and this is going to be 3 over negative 3, or sorry, no it's not. It's going to be 3 over negative 1, because negative 2 plus 1 is negative 1, x to the negative 1 plus c. So we can have 1/4 x to the power of 4. Negative and a negative make a positive, so this is going to be plus 3 x to the negative 1 plus c. Of course, we can write this again with a positive exponent. Let me just move this guy out of the way a little bit. So we can go 1/4 x to the power of 4 plus 3 over x plus c. And there we have it. You can always check by applying your derivative rule. Negative 1 times 3 is negative 3. Negative 1 minus 1 is negative 2. 1/4 times 4 is 1. 4 minus 1 is 3. So we do end up back where we started. Just another quick example here. Again, this is just our basic derivative, or sorry, antiderivative. So again, this time I have nothing in the denominator, I have nothing in a third, so we can just apply the rule. So we keep the 4 out front. X to the 2 plus 1 being divided by 2 plus 1 minus 3 x to the power of 1 plus 1 being divided by 1 plus 1 plus 5. And you may think that there's nothing here, but you can think of this like there's an x to the power of 0 here. So if I apply my rule to that, 0 plus 1 being divided by 0 plus 1. You can see it just becomes, we're going to add the x back in. And again, if we think of our derivative rule, if I took the derivative of 5x, well, y prime just equals 5. So when I take the antiderivative, I need to put that x back in. So we can simplify this. So we can have 4 thirds x to the power of 3 minus 3 halves x to the power of 2 plus 5x plus c. And then we have it. That is our antiderivative. Now, definite integrals in the applications and interpretations course, you are allowed to use your calculator for all of this. So, to do this in your calculator, we're going to go into Run Math. And we're going to want to go into our math function here. So we're going to want to hit F4. I don't want a matrix, a logarithm, an absolute value, a derivative, or a second derivative. So I'm going to scroll over to my next page, and we can see there is our integral. So we're going to click F1. And inside, we're going to enter in our equation. So I want to put it in fraction form. So I'm going to hit this ABC button. We're going to have 2 over x to the power 4. Then I'm going to scroll over until my cursor ends up in my lower bound here. So my lower bound is 1, and my upper bound is 5. So once you look, see that everything is exactly like it should be, you just hit execute. And it tells us that the area under this curve, bounded between 1 and 5, is 0.66133333. Of course, we can change this to a fraction if we wish. So this one won't fractionate. So we would just say this is equal to 3 significant figures like the IB likes, 6, 6, 1. These calculators are also really nice because you can see what this looks like visually if you use your graphing function. So another way to do this with your calculator is you go Menu, and we want to go to Graph. So I have something in my graph, so I'm just going to delete that out. And we're going to just enter in our function. So we're going to go, again, I want to enter it in fraction form. So we're going to have 2 over x to the power of 4. Again, make sure it's typed in correctly. Execute and draw. So I'm going to zoom in a little bit just so we can see the parts that we want, because we only want between 1 and 5. So I'm going to zoom in a little bit over on this side and execute. So again, I can't really see much, so if you don't like to zoom in, you can also go V window. Well, I'm going to go X min. Let's show a little bit of the negative so that we can see the axis point. Let's do max is 6. And it looks like my Y didn't need to be very big, so I'm going to zoom right in on my Y. So we're going to go back to V window. I don't know, let's go negative 0.5. and 0.5. Oops. All right, well, that gives me a little bit of an idea. So we have 1, 2, 3, 4, 5, up to 6. Maybe zoom in a little bit more. You can see it's just kind of a guessing game sometimes. I just want to get the best view we can get. All right, so we can see it a little bit more. So we're going to leave it like that. So everything in our graphing is usually in this gsolve. So we're going to go into gsolve. I don't want the root, the max, the min, the y-intercept, or the intersection. So I'm going to again scroll over until I can see my integration. First, it asks for my lower bound. Well, my lower bound is 1. So I'm just going to click 1 on my keypad, hit enter. And you can see it drew in that lower bound for us. Now it's asking us for our upper bound. My upper bound is 5. So we're going to put 5. And now it has shaded in the area that it is finding for us. Remember, that's what integration does, is it finds the area under the curve. So you can see we got the same answer here. The last example here is an integration with a bound, meaning we're going to actually solve for that value of c that we just left in the first two questions. So we have a curve has a gradient given by dy over dx equals 3x squared minus 8x, and it passes through the point 1, 3. So this is that extra bit of information that it's giving us to help us solve for c. Again, it's giving us the gradient, so it means it's already giving us the derivative. So in order to find the equation, we need to take the antiderivative. So in order to find y, I need to take the antiderivative of 3x squared minus 8x dx. Again, no radicals or surds to worry about, and nothing in the denominator that I need to worry about, so we can just apply that integration rule from above. So y is going to equal, keep the 3, x to the 2 plus 1 over 2 plus 1 minus 8 x to the 1 plus 1 over 1 plus 1, and adding in our c. So we can simplify. Again, I'm showing all of the steps. You guys may be able to see areas where you can shortcut a little bit, but I want this video to be as detailed as possible. Well, 3 divided by 3 is 1, so we're just left with x cubed. 8 divided by 2 is 4, so we're just left with x squared plus c. So this is exactly like what we did above. There's no difference between what I did here and what I did down here. Now the different part comes in, and that's when we add in this point 1, 3. So now it's giving me more information about my graph that is going to let me find that c value. So this is going to be my x value, and this is going to be my y value. So we're going to have 3 equals 1 cubed minus 4 times 1 squared plus c. Now you can see my only variable is c, so I can solve for that variable. So 3 equals 1 minus 4 plus c. 3 equals 1 minus 4 is negative 3 plus c. So 6 equals c. Now I can write down my equation as a whole. So I'm going to write the final answer in blue over here. So now we're going to put that c value back into my original antiderivative. So we're going to have y equals x cubed minus 4x squared plus 6. And now we have the full equation to the original curve. And there you have it, the 3 basic forms of integration. Integration with a bound, where you solve for c. A definite integral, where you find the area under the curve. and indefinite integrals where you're left with a c value in the end. Hope you find this useful.